Class example 215 shows a traditional problem of converting a two-dimensional cardboard sheet into a three-dimensional box. Here we see a diagram of a white rectangle which has a length of 24 centimeters by a width of 12 centimeters, and from which we will cut out 4 congruent squares. Now, we don't actually know the side length of each square, but we do know that they're squares, and we do know that they're all the same size. And this allows us to create a sort of rectangular tab on the edge of the cardboard sheet that will fold up and form the walls of the box. Now, we're asked to determine a function to model the volume of this box, and it's worth noting that having a lid or not having a lid does not change how much the box can hold. It would change the area, but that's not part of this question. So here we will find the length and width and height of this cardboard box. So we know that the original length was 24 centimeters long, and from each end we've cut out a square of length x. So our 24 centimeters has been reduced by 2x. Similarly, our width that was 12 centimeters has also been reduced by 2x. We now know our length and our width. Now if you can imagine folding these tabs up, they would each have a height of x, and they wouldn't stack, they would simply meet edge to edge. So the height of our box will be x. We will substitute these expressions in as length, width, and height, which is the volume of a rectangular prism, and there's no need to expand this function. It is worth noting that if ever this kind of question showed up in an exam, there are different representations of that function. So for example, you could factor out a factor of 2 from each of the brackets. You could multiply it out to expand it, but this is the most straightforward and helpful to the reader, I think. Now, we need to figure out the domain of this function given the context. X represents how much we've cut out of the box. And so there is a minimum and there is a maximum that will allow this to still create a box. So what's the least we can cut out? Well, if we don't cut out anything, then we don't have a box. As long as we cut out some non-zero amount from each corner, then we'll have something to fold up, and that will work. So our minimum is simply 0, and we must be greater than that. As for the maximum, the question is, at what point have we cut too much and gone too far so that we don't have a box? Well, our width is going to be our most limiting dimension. If we were to cut halfway in from either side, so if it's 12 long on the original sheet and we cut in 6 from each side, we would have no tab to fold up, like you would have no width to it. So here we have to cut out less than 6 inches from each end. This should appear when we graph our expression for volume as our x-intercepts, because what we'll see is when we are left or right of those values, the volume is represented as a negative value, which is nonsensical here. When we first type this into our graphing calculator, we don't see very much. We see a near vertical line along the y-axis, and then we see another near vertical line passing through x equals 6. So we'll have to do a little bit of work to fix our window. If we increase our y value to a maximum of 100, we still don't see that max point. I encourage you to not waste your time jumping up by small intervals. The next thing I would guess would be either 500 or 1000. Here we see that 500 is enough to show us the vertex, and so we'll work with this. Now, here I've zoomed in just for ease of the demonstration, but there really isn't any need to. As long as your graphing calculator can see that max point, it's going to be able to calculate it anyway. Using second calc maximum, we'll determine the coordinates of this local max. And excuse me, I did say vertex, but this wouldn't actually be the vertex. This is a cubic function. So we find that our max point occurs when x has a value of 2.5 and when y has a value of 333 roughly. The 333 represents our maximum volume because in this function, our dependent variable, our output, our y as it were, was volume. That x value corresponds to the height of the box and will help us determine the length and width as we sub the value of 2.53 in place of the x. Notice as we calculate our x-intercepts that we find 0, the origin, and 6 as our intercepts. This corresponds to our earlier remarks about the domain. There is a graph that exists beyond this, as you can clearly see from the calculator. It just doesn't have meaning within the context of this problem. It's important to notice that typically we're expected to show our graphs with arrows on the end when the lines continue. Here, because we do not want to consider the graph outside of this domain, we will put dots showing that these are the endpoints. And there you have it. We've represented the volume of a three-dimensional box with no lid. We've determined the x value that gives the max volume and have determined that max volume. And that will typically be all that's asked of us. As I mentioned earlier, we can use that x value to determine the actual measures of the dimensions, which is to say the height is 2.54, the length is 24 minus 2 times 2.54, and the width is 12 minus 2 times 2.54. And if you multiply those three values together, you should get 332.6.